Hello everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is primary injection testing of low voltage circuit breakers. My name is Greg Valdez, and I'm the Marketing Communications Manager for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NITA CTD and one PDH or 0.1 CEU for attending. After today's presentation, you will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of this webinar, if you'd like to watch it again at a later time. Or you can also share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Sanket Bolar, Megger Substation Application Engineer. Also, to assist with the Q&A session, we will also have 2 panelists join us today. Dinesh Shajer is a manager for our Megger Technical Support Group, and Volny Naranjo, he was also a Substation Application Engineer. Okay, let's get started with our presentation. Thank you for joining us today, Sanket.
Thanks, Greg. Good morning, everyone. So in today's presentation, as Greg said, we are going to be talking about primary injection testing of low voltage circuit breakers. So this is how we are going to go about the presentation. We're going to start off by talking a little bit about circuit breakers. Then we're going to talk about some of the tests that are done on low voltage circuit breakers. After that, we are going to focus on primary injection testing. We're going to talk about some of the challenges that people face during primary injection testing. Then we're going to talk about how the advent of technology has improved certain aspects of primary injection testing. All right, so let's get started with the first section. So what are circuit breakers? Circuit breakers form the arm of the protection system, I feel. CTs, PTs act as the eyes of the protection system. So the CT sees the fault current and feeds it into the relay. The relay is the brain of the protection system, and the relay operates the breaker, which isolates the fault by interrupting the current. There are various definitions for circuit breakers given in various documents and standards. We'll go with the NEC and NEMA definition, which says circuit breaker is a device designed to open and close a circuit by non-automatic means and to open the circuit automatically on a predetermined overcurrent without damage to itself when properly applied within its rating. So circuit breakers are used in various applications, but there are some characteristics that run common to all the circuit breakers. Let's discuss some of them. The frame is the main mechanical part which provides the support and strength to the circuit breaker. Circuit breaker deals with high currents interrupting them, so it needs a support structure to keep it from falling apart because high currents generate a lot of forces. There are 2 types of frames. Low voltage power circuit breakers typically have metal frames, and MCPs have a frame made up of molded insulating material such as glass polyester or thermoset composite resins. The trip unit is the brain of a breaker. Trip units can be either electromechanical or electronic type. Electromechanical trip units work on the thermal magnetic principle. You have a diagram here showing how the thermal magnetic principle works. So if you follow the pointer on the screen, you'll see that on this diagram, there is a part here marked by the number 5. That's the trip bar. That's the bimetallic strip. And the part number 7 is the electromagnet. The bimetallic strip is the thermal portion of the trip unit, and the electromagnet is the magnetic portion of the trip unit. So how do these two portions work? Let's look at the diagram given over here to see how the thermal portion works. So when you have a thermal overload condition where there is a current, a high current flowing through the circuit, the bimetallic strip will heat up. The bimetallic strip is made up of two metals which expand at different rates when heated. So that will result in the strip bending because of heating, and this part that you see here on the end of the strip will hit the trip bar, thus releasing this latch, and the contacts will open. That's how the thermal portion works. Now let's look at the magnetic portion of it. So you have an electromagnet connected in series in the circuit, and when you have short circuit currents of really high magnitude flowing in the circuit, those currents will result in a force, magnetic force being generated in the electromagnet, which will pull the armature towards it. As the armature is pulled, the trip bar rotates, thus releasing the latch, and the contacts of the breaker open. Electronic trip units work in a slightly different manner. They have different parts. They have current sensor, they have circuit boards, which is the brain, they have flux transfer shunt trip. So in electronic trip units, analog or digital processing of the samples of the signal is done, and the current sensor serves as the eye. It's like a CT. It picks up on the current and provides a signal in the form of current or voltage to the trip unit. Both of them don't require any external power. Electronic trip units may need external power for some functions. Then you have the contacts and the operating mechanism. There are two main types of operating mechanism. There is over toggle mechanism, which is what you typically see on MCBs or MCCBs. What it means is that there is a handle with which you can either open or close a breaker. When the handle goes over toggle, that is when it goes past a point of no return, then the contacts operate. The actual time that the contacts take to open or close is independent of the speed with which you move the handle. Then there is the two-step stored energy mechanism, which is used in low voltage power circuit breakers, where there are separate springs for opening and closing of the breaker. So you can actually charge the spring for closing a breaker even before it has opened. So what that does is that gives a reclosing ability to the breaker. So if the breaker opens in the case of fault, it can be immediately reclosed remotely. Then you have the arc quenching method. When the current is interrupted, an arc is created, and that arc needs to be extinguished quickly for the safe interruption of the current. Now, this arc quenching is done by using various techniques. One of them is stretching the arc. The arc is stretched by moving the contacts apart. So when the contacts move further away, the arc gets stretched and it weakens to the point where it gets extinguished. Then you have breaking the arc, where the arc is broken up by using arc shoots. You have blowing out the arc, where the arc is blown out by using blasts of compressed air. Then you have enclosing the contact, which works on the principle that an arc needs oxygen to sustain itself. So if you take out the supply of oxygen, then the arc will extinguish. This can be done by introducing dielectric media like oil or SF6, or by having no media at all, that is vacuum. On the basis of voltage rating, they are classified into three types broadly. There's high voltage breakers, which are rated for voltages greater than 72.5 kV. There are medium voltage breakers, which are rated between 1 kV and 72.5 kV. And then there are low voltage breakers, which are used at voltages less than 1 kV. Low voltage breakers are further classified into miniature circuit breakers, which is what you typically see on the distribution panels at your homes. Molded case circuit breakers are used in relatively low current applications in industries. Then there are power circuit breakers, which are the big rack and rack out breakers that you see here on the right. These are used in industries as well. Certain tests are done on high voltage breakers and medium voltage breakers, but like timing and travel analysis, for example, but we are going to focus on low voltage breakers here. So let's talk about some of the tests done on low voltage circuit breakers. So before we get into the actual test, let's talk about why we need to test circuit breakers. So circuit breakers, as I said, they form the arm of a protection system. They isolate the fault. They protect the system from faults. They limit the outage area by if they have the right selective coordination, they can limit the outage area to a minimum. Unreliable operation of the breaker can be in two forms. It can trip when it's not supposed to, or it may not trip when it's supposed to. The latter is called the dependability of a circuit breaker. So a dependable circuit breaker should trip when it's supposed to. If it doesn't trip when it's supposed to, what will happen is that will result in injury to personnel, it will result in damage to equipment and property, it will result in the outage area being more widespread. If the breaker trips when it's not supposed to, it's said to lack security. So if it does that, it will result in expensive downtime. So either way, if the circuit breaker doesn't operate reliably, then that results in losses. When you test a circuit breaker, you will look at the nameplate and you may see some terms that you may not be familiar with. Let's get familiar with some of the terms that you would come across while testing a low voltage power circuit breaker. So this is what the nameplate looks like. You would see voltage. Voltage is the highest RMS voltage at which the breaker is designed to operate. And there is frame rating. Frame rating is the maximum continuous current rating for all parts in the breaker except the overcurrent device. The overcurrent device can be rated for a current much less than the frame size of a breaker. So you can have a breaker with a frame size of 1200 amps having an overcurrent device rated for 300 amps. Interruption rating or interrupting rating is the highest current at rated voltage that the device can interrupt without external damage. Control power, if the breaker has, it needs to be electrically open or closed, it has a motor to charge the closing springs, it's going to need external power. Now let's talk about some of the tests done on low voltage circuit breakers. Insulation resistance, so the insulation between the conducting path and ground needs to be checked, and that is done by using an insulation resistance test set. So you can apply a DC voltage of typically 500 volts or 100 or 1000 volts across the poles with the breaker closed, between the pole to ground with the breaker closed, or you can also check the insulation across contacts by with the breaker open. You can either go with manufacturer's limits, if not, the stable that's been taken from the NETA standards gives you a reference limit. It applies to, as you can see, it applies to electrical apparatus other than rotating machinery and can be applied to power circuit breakers as well. Then you have individual pole resistance measurement where you check the conducting path itself. You want to make sure that the contacts are in good condition, that there are no loose connections inside the breaker. Any of that, if there's a problem in the conducting path, that will result in a high resistance. If there is high resistance, what that means is that the conducting path is not good enough. And if there is high current flow through the breaker, then that can result in heating, resulting in damage to the circuit breaker. So the pole resistance is an important parameter to check. If there is a deviation by more than 50% of the lowest value measured on adjacent poles or similar breakers, then it needs to be investigated. The resistance measured in this case is really small, so you need special low resistance ohm meters. DC current is injected through the breakers, and the voltage drop that's measured is typically in millivolts. The readings could be as low as microohms. So you also have some other tests like the secondary injection test, where the current is injected into the trip unit itself, and the logic of the trip unit is checked at different calibration points. In this case, the breaker may or may not trip, but the wiring and the current sensors are not checked because you're not actually injecting current through the breaker. The test sets that are used for this test are sophisticated but really small as compared to primary injection test where the test sets need to be really big because you're actually going to be injecting current through the breaker. So when you do a primary injection test, you check the breaker operation and you check the trip unit logic because you're measuring the trip times and you're making sure that they are within the tolerance limits given in the time current curve for the trip unit. You're also checking the wiring and current sensors. So this is what I call a complete test. Now let's focus on primary injection testing in the next section. What do you need when you do a primary injection test? Because you're going to be playing with high currents, you need a high current source. The current needs to be injected in two forms, continuous form and pulsed form. You need connections to connect the test set with the breakers. You need to have a good knowledge of the trip unit. You need to be able to know how to operate the trip unit to set the right delays and the pickups required to do the test. You need to understand the time current curves to be able to validate the results that you get. There are 4 types of tests that are done as part of primary injection testing. There is long time test, there is short time test, there is instantaneous pickup, and there is ground fault. Let's talk about each of them. So you have the long time test. The long time delay characteristic provides protection against overload conditions. This is a case where the current may increase, but it may not go up to a level seen in short circuit conditions. The current can result in eventual heating up of the breaker. So in this case, typically there will be a delay of a few seconds, but eventually the breaker will need to trip. The test current typically injected to test the long time delay is set at 1.5 to 3 times the pickup level. The pickup level for the long time test is set pretty close to the rating of the overcurrent device. So the test current is set at 1.5 to 3 times the pickup for electromechanical devices, twice the pickup for solid state devices. The minimum time delay band is selected. And to do this test, you would inject the current continuously and then record the trip time. The trip times are typically in the range of 10 to 50 seconds. Each pole needs to be tested separately because these test sets are usually single phase test sets. The manufacturer's time current curves need to be used to validate the results. So let's look at a long time delay characteristic and see how we can interpret the results. So in this case, for example, in this diagram, you can see both the long time delay characteristics and the short time delay characteristics. Long time delay characteristics, the one given this region. So you can see that there are 4 bands here, LTD band 1, 2, 3, and 4. Band 1 has the lowest trip time and band 4 has the highest trip time. So as we said in the previous slide, we would select LTD band 1 on the trip unit. The pickup has been set at 1 times the rating of the overcurrent device. As you can see, it says 1.0x here. So since the pickup has been set at 1.0x and the pickup is denoted as C, as we said in the previous slide, we would inject a current of twice the pickup value. So to find out what the time limits are for LTD band 1 at the test current, we will draw a vertical line which intersects the horizontal axis at 2 times the pickup value, that is 2C. The 2 points at which the 2 points on LTD band 1 at which the vertical line intersects are the trip time limits for that particular test. So the max time in this case would be 30 seconds. The minimum time in this case would be 20 seconds. So to pass the test, the breaker will need to trip in a time between 20 to 30 seconds. If it trips earlier than 20 seconds and if it takes longer than 30 seconds to trip, it means that the breaker has failed the test. Now let's look at the short time delay characteristics. Short time delay characteristics are provided for protection against short circuit or fault conditions, but an intentional delay is introduced here. Could be for coordination or for situations such as motor starting, where the motor can draw high current for a few cycles in the beginning. The test current is set at 2.5 times the short time pickup. The short time pickup could be any of the settings on the overcurrent device. The maximum time delay band needs to be selected. In this case, just as the long time test, continuous current is injected and the trip time is recorded. The current is higher and the trip time is lower in this test. Each pole needs to be tested separately. The time current curves can be used to validate the results. In addition, a current less than the pickup needs to be injected for a period less than 1 second, and it should be verified that the breaker doesn't trip at that current. So let's say we set the pickup value at 1.5 times the long time pickup. So 1.5 times C. The short time delay band is set at I square T in. So if you look at the short time delay characteristics here, you'll see that there are two responses. There's I square T in and I square T out. What I square T in means that the trip time is dependent on the magnitude of the current. So higher the current, lower the trip time. As you can see, the band has a slope. On the other hand, if you look at I square T out response, you can see that the bands are horizontal, which means the trip time is independent of the magnitude of the current. So if your response is I square T out, doesn't matter if you're injecting 3 times the pickup, 3 times C or 6 times C, you're going to have the same trip time limits. So let's select the maximum time delay band in this case, that's I square T in. The pickup selected is 1.5 times C. 1.5 times C is the pickup. You're going to be injecting a test current which is 2.5 times the pickup value. So 2.5 times the pickup value is 2.5 times 1.5 times C, which is 3.75 times C. So you will draw a vertical line intersecting the horizontal axis at 3.75 C here, and the 2 points on the I square T in band where the vertical line intersects are the trip time limits for that particular test. So the maximum time in this case will be 1.5 seconds. The minimum time will be 1.0 seconds. Now let's look at the instantaneous test. In instantaneous test, the instantaneous trip characteristic is provided for short circuit or fault protection. There is no delay here. The breaker is supposed to trip as soon as the current crosses the pickup value. To run this test, pulses of current are injected as opposed to continuous current. The duration of the pulses are typically between 5 to 10 cycles, and you can start off at 70% of the expected pickup, and you can inject repeated pulses with increasing current magnitude at regular intervals until the breaker trips. The current recorded should be within tolerance levels. Typically, the tolerance levels are plus minus 10% to plus minus 25%. The best source is, of course, the manufacturer's tolerance levels. Each pole needs to be tested separately. The pickup values for instantaneous tripping are set the highest. They're typically either 8 times or 10 times. Ground fault test. This test can be done on breakers with electronic trip units where ground fault protection is enabled. First of all, if you have a trip unit like that, you need to disable the ground fault protection to be able to run the other tests, because the pickup value for ground fault is the lowest. So if you try to run another test with this enabled, the breaker will trip on ground fault. If you don't have the ability to disable the ground fault protection on the trip unit, you can run the other tests by connecting the 2 poles in series, as shown in the figure. So when you connect in this manner, the currents that flow through the 2 adjacent poles are in opposing directions, and the resultant current measured by the ground fault CT is 0. So the breaker doesn't trip on ground fault. In this case, just as a long time test, we inject a continuous current and the trip time is recorded. The current magnitude is low and the trip time is low as well. Each pole is tested separately. The test current is set at 2.5 times the pickup value. The maximum time delay band is selected, and the time current curves can be used to validate the results. So let's look at the time current curve for a ground fault test for the same trip unit. So you again have two responses here, I square T in and I square T out. In I square T out, just as the short time test, you have three bands, max, int, and min. Max has the highest trip time limits, min has the lowest trip time limits. So just as we said in the previous slide, we are going to use a test current of 2.5 times the pickup value. So we're going to draw a line which intersects the horizontal axis at 2.5 times the pickup. The 2 points on the I square T in band at which the vertical line intersects the band are the trip limits. And in this case, the maximum time is 0.5 seconds and the minimum time is 0.35 seconds. You can see that the band is pretty narrow. So these are the 4 tests that are done as part of primary injection testing. Some points that you need to make a note of is that if you have really long cable connections at the input, what that will do is that will result in a voltage drop on the input side if you are drawing a high current. If you're doing the testing at high currents, high output current means high input current for the test set. And if that high current flows on the input side through really long cables, then there will be a voltage drop, which will result in lower input voltage on the test set. Lower input voltage means reduced output from the test set. So that's something that you need to take note of, to make sure that the cables are only as long as they need to be, and they are the right size, of course. While testing breakers with thermal trips, a sufficient cool down time is required. For testing of MCCBs, NEMA AB4 says that if you're going to repeat tests on the same poles, you need to wait for a period of 20 minutes between tests. If the breaker is equipped with an undervoltage trip release, the trip release needs to be energized to ensure proper operation of the breaker. So if the breaker has an undervoltage trip device, the undervoltage trip device will trip out the breaker if the voltage on the device drops out. So you need to make sure that that's taken care of. You can run into some challenges while doing primary injection testing. One of them is input breaker size. This is a question that I run into quite often with our customers. That is, what breaker size do I use? Now the spec sheet of the test set will give you the breaker size, or will give you the input current based on the maximum output of the breaker. That may not be what you need. Depending on your selection will be based on the highest rating of the breakers that you're planning to test. The input current and the output current have this sort of a relationship that's represented by the figure given here. The input current is proportional to the square of the output current. So the efficiency of the test set drops with increasing losses, which are primarily I square R losses, right? That explains the relationship between the input and the output current here. So the selection should be made based on the input currents expected while testing the breakers that you have. So that the numbers that you arrive at can be much lower than what the spec sheet says. So when you use these high current testers, these high current testers deal with really high current, but they have really low compliance voltages. If the impedance of the circuit is high, if you're using really long cables that can result in high impedances, then the compliance voltage may not be enough to inject the test current. How do you deal with this situation? There are different ways of dealing with high circuit impedance. Some test sets have high voltage, low current tabs. If you can run the test using those low current tabs, then you can use those tabs for running the tests on circuits with high impedance. Then there are some test sets which have multiple sources or multiple current modules, which are usually connected in parallel. Those sources or modules can be connected in series so that you get a higher compliance voltage. But in this case, what happens is you get a higher voltage, but the current capacity reduces. So for example, if you have two sources which are connected in parallel normally, and the compliance voltage is V, the current capability is I. If you connect those two sources in series, now you'll get a compliance voltage that is twice of V, but the current capability will be reduced to half of I. The circuit impedance can be reduced by reducing the length of the connections. You use shorter cables, you connect multiple cables in parallel. As you can see here, resistance is directly proportional to the length of the cable, inversely proportional to the cross section. You don't want to use too thick cables because that will increase the depth of the conductor, increasing the inductance of the circuit. You can use multiple conductors in parallel. If you use too many conductors in parallel, though, that results in the cables being too heavy, and that can make testing cumbersome because connections between the test set and the breaker gets difficult if the cables get too heavy. If you're going to be using really long cables, then the cables carrying opposing currents can be twisted together as shown in the figure. So what that does is the currents flowing the opposite directions through those cables cancel each other out. The fields of the currents cancel each other out, so that reduces the inductance of the circuit. One good way of eliminating circuit or minimizing circuit impedance is by eliminating cable use altogether and going for stab sets. The challenge here is having the right stab sets on your test sets that are compatible with the stabs of the breakers, because breakers comes in various shapes and sizes. They have all sorts of stab sets. They can have vertical stabs, they can have horizontal stabs. The stabs can have single set of finger clusters, double sets of finger clusters. They can be round stabs or socket stabs. So having the right stab set for the range of breakers that you have can be a bit of a problem. Now let's talk about some of the recent advances in technology and how it has affected primary injection testing. As far as the technology goes, the traditional technology which has been around for a long time is the one shown on the left. You can see that there is a gating device to control the firing angle of the voltage, and then there is a variac that feeds into a step-down transformer. You have a CT connected on the output, which gives you the current being put out by the test set. On the right, you have the newer technology which makes use of solid-state technology, and then there is a feedback loop between the CT on the output and the brain of the instrument. There are various aspects of primary injection technology. We'll see how technology has helped in those various aspects. Let's start off with DC offset. So DC offset is an asymmetry which is observed in the first few cycles when current is suddenly injected in an inductive circuit. In an inductive circuit, the current is supposed to lag behind voltage. So if you switch on the voltage at voltage 0, for example, the current also starts from 0. As obviously the circuit was an open circuit and you're suddenly closing it, so the current is going to start from 0. Now that is in contradiction to how an inductive circuit should behave. This contradiction gives rise to this behavior, and you see an asymmetry in the first few cycles. The level of this offset or asymmetry is dependent on the X by R ratio of the circuit. X is the reactance of the circuit, R is the resistance, and also the point on the voltage wave at which the circuit is closed. The way this offset can affect your primary injection testing is during instantaneous tests, where if you have a really high peak because of the offset, then the trip unit that responds to peak values can trip the breakers, or even trip units that read the RMS value will read a higher RMS value than what it should be, and they can result in the tripping of the breakers. So it can result in incorrect instantaneous pickups being recorded. So to get accurate results, the asymmetry needs to be controlled. Let's look at how we can control the asymmetry. The asymmetry can be controlled by changing the firing angle. So this is the effect that the voltage firing angle has on the DC offset. Voltage firing angle is the point on the voltage wave at which the circuit is closed. You can see that as the firing angle moves from 4 degrees to 70 degrees, you can see that the DC offset goes down considerably. The DC offset is measured by looking at the difference between the peak divided by √2 value and the RMS value. For a perfectly sinusoidal wave, both of them will be equal, as peak by the square root of 2 is actually the RMS value. But as the voltage wave becomes distorted, both of them will move further apart as the peak increases. So you're going to see a higher difference when there is more asymmetry. As you can see in the figure, the peak by √2 and the RMS are closest to each other when the firing angle moves in the range of 60 to 70 degrees. So as I said earlier, the offset can be determined by measuring the difference between the peak divided by √2 and the RMS value. So the way to deal with this situation, if you have a test set using traditional technology, is you would look at the peak by √2 and the RMS value, and then you would change the firing angle on the test set, look at the peak by √2 and the RMS value again, see if the difference has increased or decreased. So you would play around with the firing angle repeatedly until you arrive at a point where the difference between the peak by √2 and the RMS value is at a minimum. And that would be the firing angle which would work the best for you, and then you can proceed ahead with the test that you're doing. The test sets which use modern technology, those test sets, the X by R ratio of the circuit is calculated by the test set by injecting a low current initially. So from that X by R, the test set determines the firing angle that is required to eliminate the offset completely, and that's how the newer technology deals with this problem. Here's a comparison of the waveforms from test sets employing traditional technology and modern technology. So on the top left, you have this figure where you can see that there is considerable offset in the first cycle. You can see that the firing angle is 4 degrees in this case. As the firing angle is brought to 60 degrees, you can see that the offset reduces considerably, even though there's a little bit of it present in the first cycle. And on the right, you have a figure you have a waveform capture from a test set employing modern technology, solid state technology, where you can see that the offset has been eliminated completely. So all 5 cycles are completely alike. Setting the target current. In the test sets from the olden days, the current control is completely manual. So you have a variac, you could have a coarse switch for coarse adjustment, and the variac does the fine adjustment. But the current control is completely manual. So if you have to do the test at a particular current, to be able to find out at what setting the test needs to be done, you need to inject repeated current pulses until you get the pulse of having the magnitude at which you have to do the actual test. And then you can start the actual test by injecting that test current in continuous mode. In modern test sets, the impedance of the circuit is determined by the test set. So the test set injects a low current before it starts the actual test, and it determines what the impedance is. From that impedance, it gauges the voltage that is required to inject the test current needed to do the test. Automatic current regulation is important, especially in long time tests involving really long durations and high currents. So in these cases, what will happen is because of the circuit heating up, the current output of the test set will start to drop. And if the output is not adjusted, if it's kept fixed, then that will result in the breaker taking longer times to trip because the current has become lower. That will result in incorrect trip times being recorded. So how do the two technologies deal with this problem? If you're using a test set with traditional technology, you would need to continuously adjust the output to keep the current close to the target current. If you're using a test set employing modern technology, the test set will take care of that for you. So there's a feedback loop, as I mentioned in one of the earlier slides, where the instrument knows what current is being put out and it adjusts the output so that the current sticks to the target current. Time current curves form an important part of the test. So to validate the results that you get, you need to look at the time current curves from the trip unit manual. If you're using a test set with traditional technology, there is no software. So you obviously need to pull up the time current curves and you need to plot the test points on the time current curves, see if they fall within the tolerance limits to make sure that it's a pass. If you use a modern test set which has a software, and the software takes care of that for you. So the software could have a time current curve library with curves for hundreds of breakers. You can even put in the curve that you want if your breaker is not in the database. So you can pull up the time current curve, run the test. The test points are plotted on the time current curves by the software. The software even indicates whether the points are a pass or a fail by highlighting them in green or red. So it eliminates the chances for operator error in this case. Another chance for operator error is if you have to write the entries, the readings that you get on a report, as opposed to the software generating the report automatically for you. Especially for users who are not really familiar with primary injection testing, if they're new to all these terms, long time delays, short time delays, pickups, if they don't know how to interpret those terms, how to actually go about testing, there's every chance of an error occurring in noting down the readings on the report. Another way in which technology has made it easier is solid state technology means that the size and the weight of the test sets have reduced. One example is this case where both of these test sets are have the same specifications as far as current capabilities go. You can see that one unit is smaller and much lighter than the other. The delays and the pickups that I recommended in when I talked about primary injection testing are taken from ANSI C3750, which deals with low voltage power circuit breakers used in enclosures. Also, some of the references that I made for limits, they're taken from NEMA AB4, which deal with MCCVs. Then certain limits were also referred from the NETA standards. As far as high current testing goes, there are all sorts of breakers. They come in various shapes and sizes. So depending on your requirement, you would need to use different test sets, right? When I spoke about then versus now, then doesn't mean that the technology is obsolete. The technology is very much relevant today, because in cases where the breaker capacity is very high, the traditional technology has worked for decades and it will continue to work. Efforts are being made to get the test sets with modern technology to work at those high current levels. As far as what we have to offer now, you can see that if you have to test breakers for up to 3000 amp rated breakers, you can get a DDA 3000. Then there's a DDA 6000, which you need to get to be able to test breakers rated for up to 6000 amps. Both of them look very similar. They're pretty heavy set, as you can see. DD1600 is smaller, and it's rated to test for up to 1600 amp breakers. Then you have the Odin, which can test up to 2100 amp rated breakers. It can be moved around in a cart, so it's portable. There are current modules in it. You can use 1, 2, or 3 modules depending on your current requirements. And then you have the SPY, which employs modern technology, modern solid-state technology. It's primarily meant for MCCBs. You can use it for, it's rated, each unit is rated to test for up to 225 amp breakers, but you can test higher amp capacity breakers by using multiple units in parallel. These can be daisy chained and can be operated in parallel to achieve higher currents. That's the end of the presentation. If you have any, we're going to be getting into questions the next couple of seconds. Greg?
All right. At this time, as Sanket mentioned, the presentation portion of the webinar is officially concluded. We'll take around 30 minutes to answer as many of your questions as possible. Again, if you have any questions, please submit them now in the Q&A box on the right side of your screen. For those that are leaving our presentation, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there is a field where you can also request a demo or quote on any of our Megger products. Again, a copy of this presentation, along with a link to the video recording of the webinar, will be emailed to everyone within a few days. You can also view video recordings of our previous webinars on our website at us.megger.com/webinars. And you can also register for next month's webinar, Turns Ratio Testing, Principal, Operation, and New Measurement Techniques, that's taking place on February 15th at 10 a.m. Central Standard Time. Our presenter will be Aaron Tucker, one of our Megger applications engineers. All right, now let's go and get to your questions. Now, first question is, primary injection tests the trip unit and its trip coil. How do I test electrically operated breakers that have closing and opening coils as well? That is, how can I electrically operate them and check the closing and opening times?
So the question might be interpreted as in two different ways. So for low voltage circuit breakers that will have those coils, if you just want to test the breaker on the coils, well, there's another technique that is the secondary injection test. And for that, you need specific accessories for the breaker. You need proprietary equipment or testing equipment by the manufacturer of the breaker. So you will have to have different testing equipment for different breakers. Now, if you're thinking about high voltage or medium voltage breakers, then that you can use what is called a circuit breaker analyzer. And in those, you will be sending a control command to the coil, and at the same time starting the timer to measure how long it takes for the main contacts to operate. So that is the way to test the high voltage and medium voltage breakers. Thank you.
All right, thank you, Volny. All right, the next question is, since electronic overloads are common to all 3 poles via separate sensors, is it necessary to run all tests on all 3 poles, or just run all tests on 1 pole and run 1 test on each of the other poles to verify proper operation?
That's a very good question, because obviously if we can cut down the number of tests, it would certainly help us improving the efficiency and making sure that we get the job done quickly. But think of this from a system standpoint of view. When we talk about primary injection testing versus secondary injection, you can, let's say if you do the secondary injection testing, you can still verify that, okay, the trip unit is working, but in reality, you're not checking the complete system, which is the breaker operation and the operation of the trip unit. So similar is the answer for the question that is being asked, that when you talk about electronic loads, yes, there would be a lot of symmetry between the three phases, but if you want to make sure that all the three phases the sensors are working right, all the three phases are operating around about the same time, there is no lag between the one and the other phase, it is recommended to test all the three poles, and you should perform all the tests that are recommended. So our recommendation is that you should run all the tests on all the three poles to give you the most accurate condition assessment of the breaker under test.
All right. Our next question is, how are cables from the test set connected to the circuit breaker when the circuit breaker is installed?
So as shown in the presentation, connecting to the circuit breaker is one of the key points of the test. If you don't have a good connection, you will have a high impedance, and that will difficult your test, or make probably not, you're not going to be able to test it. So you have to have short cables, and then you have to have very good connection and tight connection. So the question is a very good question, because sometimes, well, you need to be efficient while you're testing. You need to speed up the test, and the accessing the breakers or removing them from whatever they are connected will reduce or increase the time of testing. And so you definitely, it's a question that doesn't have a unique answer. There's no unique accessory to be connected to all of the breakers in any situation. So for every specific case, you have to look for a solution on how to efficiently connect to the breakers. There's some accessory that you can use that you don't have to connect directly, or you don't have to do a tight connection or bolted connection. You just press a gun or a probe to the breaker on one side, and then the other side is connected. It's a fixed connection for all the breakers. So that will speed up the testing, but still you might have a high impedance there. So sometimes you need to connect directly to the breaker. There are also, when you are testing circuit breakers, there are kind of big, high amperage, and they're of a good size of dimensions. The rack out breakers, they will definitely have to go outside the rack, and then you have stabs that you will use to connect to the primary injection test set. So it's basically a direct connection from the terminals of the unit to the terminals of the breaker with a piece of bar, very short piece of bar. So there's different solutions, and there's no unique answer for that. It's basically something that needs to be worked in the field when testing.
Okay, thank you. Next question. How do you regulate current real-time and primary injection?
So if you're using a test set with traditional technology where the current control is manual, you would need to change the current real time by changing the variac on your test set. You'll be able to see the current on your display in real time, and you just need to change the variac such that the value comes close to the current at which you want to do the test. If you are using a modern test set with solid state technology where there's a feedback loop, the instrument knows what current is being put out, so the instrument takes care to make sure that the current sticks to the target current and doesn't deviate from it.
All right. Next question is, what equipment is recommended to make the primary injection?
I'm not quite sure if I understood your question, but as I said earlier, you need a high current source to run a primary injection test, and the type of test set, the size of the test that you get will depend on the size of the breakers that you will need to test.
All right, with current improved technology, is it really required to test low voltage molded case circuit breakers? If yes, what should the frequency be of such a testing program?
So the answer is yes. Molded circuit breakers are really important, and you can think about hospitals, you can think about data centers, you can think about production lines with motor control centers that are motors that are really important for a production. And the circuit breaker is a really important piece of the system on any of these situations. So it's a part of the maintenance, and you want to test them and be sure that they are going to operate or do not have false operations. In regards to the frequency, that depends on the facility and the maintenance programs. I've seen testing programs every 2 years. I've seen also testing programs every 5 years, or in some situations I've seen every year. So it's more like an internal criteria depending on the criticality of the loads and the systems that you have, and also on the resources.
Okay, next question. Is primary injection testing a destructive test?
Okay, so the question is kind of valid, that when you're trying to run the test, you are injecting a huge amount of current through the breaker. But if you think about it, and if you look at the breaker timing current curves, the breaker is supposed to handle those kind of current for a short period of time. One thing to note in this one is that when you're running this test, the breaker trips really fast based upon which test you are running. For example, if you're running an instantaneous test, you are talking about a matter of cycles. If you're running a short time test, the breaker would trip in like few seconds. So you are not injecting a huge amount of current for an extended period of time. So running a primary injection test, even though the current is high, but it's very safe to run this test. It won't cause any reduction in the life of the operation of the circuit breaker. And that's the reason why this test is recommended in the IEEE standards, in the NETA standard, in the NMAX standard, which most of the nuclear regulating agencies follow. So this is a test that is very common, and you would not take any life out of the breaker if you do this test.
Okay. Next question. Could you please go over the short time pickup? Not sure where you get the STPU value. Also, if the short time is set to 0, is it the same as the instantaneous?
So trip units have a long time pickup, they have a short time pickup, they have instantaneous pickup. The short time pickup can be set as various options. It can be selected as a multiple of the long time pickup or of the rating of the current plug. So you can select any of the settings that's provided on the trip unit. You don't have to stick to a particular value. And the test current, as recommended from the standards, will be a certain multiple of the pickup value itself. So the STPU value, you would actually see it on the trip unit itself, on the manual of the trip unit or on the display of the electronic trip unit. You'll see various options, and you can pick one of those to run your test. As far as the short time delay is concerned, no, it cannot be set to 0. You can select from different options. You can select between different bands. As we saw in the example earlier, there was I2T in or I2T out. If you had selected I2T out, you could select max, int, or min. So there are different options to choose from, but there is always a delay when you're dealing with short time delay characteristics. So there's always going to be a delay. It's going to be a very short amount of time, less than a second maybe, but there's always going to be a delay. It's not the same as instantaneous. As I just said, when you're dealing with short time characteristics, there is an intentional delay, however short it may be. But in instantaneous, the breaker is supposed to trip instantaneously as soon as it reaches the pickup value, as soon as the current reaches the pickup value. So these are two different things. The short time delay pickup is usually less than the instantaneous pickup. So the pickup is the instantaneous pickup is set higher, because obviously if you want to introduce a delay on short time, then you don't want the breaker to trip at a current lower than the short time pickup.
Okay, the next question is, should we read peak or RMS for instantaneous tests?
So that depends on the trip unit of the breaker. As I said earlier, some trip units respond to the peak value of the current. Some trip units take samples of the current signal and measure the true RMS. So if you want to do the test the right way, look at how the trip unit measures the current and select the acquisition method accordingly.
Next question is, how often should your primary test set need to be calibrated?
So industry standards about calibration for most, for pretty much every test equipment is every year. And but keep in mind that calibration might just be a verification, not an actual adjustment of the output parameters of the unit. You just need to verify that it is in compliance with the specs of the unit and what you need from the unit. So sometimes that calibration can be done by a company that is close to you, or you don't need to send the equipment too far. And if that verification needs to also adjust some of the internal parameters or anything inside the unit, then you need to probably send the unit to the manufacturer, to an authorized service center.
All right. Next question is, what voltage is the test set putting out, and is it necessary to inject the current at the breaker's rated voltage?
Okay, so the first part of the question, this test that we are talking about, primary injection testing, the idea of this test is to perform the test at high current and low voltage. So when we're talking about this one, the test set might have an open circuit voltage of either 6 volts. If you connect the stabs in series, you might get 12 volt. But typically, you are talking about very low voltage in the range of like 10 volt or less. The second part of the question is talking about, should you be performing the test at rated voltage and the current required to trip the breaker? That is what we call as factory test. Out in the field, you don't have the luxury of 6,000 amps at 480 volt. That's just going to be a huge amount of power source that you need to have. So typically the test is performed at high current and less voltage. To your question, is it recommended or should we perform the test at rated voltage? That kind of test would be destructive, because then you are kind of doing the test at both high power, high voltage and high current. And typically that's the test that we call as a kind of destructive test, and that's the reason why in the factory at OEM place, what they would do is that in a full batch, they would randomly pick few breakers and they would test at rated voltage and rated current to make sure that the insulation is of right strength, the poles are separated apart, they can handle the current, those kind of things. So as I said, like out in the field, you perform the test at high current and low voltage, and those tests are non-destructive tests.
All right, the next question is, I had a plant engineer complain that primary injection of his molded MCCBs, molded circuit breakers, he claimed was followed by a high failure rate, so he didn't want to test them anymore. Any thoughts on that?
That's a very interesting question because in order for us to kind of answer that with some reasonable justification would be to understand what kind of failures are we talking about. Remember, when we talk about circuit breaker, you could have different types of failures. There could be a problem because of the heating that could lead to some problem with the contacts. There could be insulation failure, or there could be that the breaker couldn't handle the amount of current that it is supposed to handle. So understanding what kind of failure those breakers had, that would give a little bit more insight. But in general, what has been seen is that primary injection testing does not or should not affect the life of the breaker. And in addition to your primary injection testing, you should also be doing a contact resistance test, as Sanket mentioned, to measure the amount of contact resistance, which would in turn tell you the amount of heat losses in the breaker when it's carrying the fault current. And then also the insulation test to make sure that there is a desirable amount of insulation between the poles and poles to ground.
All right. Next question, is reducing instantaneous settings on a circuit breaker still a valid test? For example, a 12-time setting of 52,000 amps instantaneous is tough to get in field situations. Is reducing the setting to 4 times valid?
There is no standard that mentions that the instantaneous trip needs to be a certain level. When we spoke about the other tests, I did mention about the delay band being minimum or maximum, or the pickup, the test current being set at a certain multiple of the pickup value, but there is no such thing provided in the standard C3750 for the instantaneous pickup. So it would still be a valid test, and just as you said, if you don't have a big enough field test set to get that current, then you'll obviously need to reduce the instantaneous pickup. The ideal thing is to keep it as close to what it would be set at when it's in operation. But if it's not possible to achieve that level of current using your field test set, then you will need to reduce the pickup to a smaller value.
Okay, I guess Sanket appropriately answered that question. I just want to add one more point to that question, that what the question is asking is something that is being done out in the field all the time, because the amount of current that you can get from any certain given instrument may not be enough for you to test at the trip settings of that breaker. So it is kind of quite common for people to do what you're asking, and it has been kind of industry practice that it is acceptable. But as Sanket mentioned, that the ideal scenario would be to either do at the trip settings or close to it. But what you are trying to do is something that is kind of accepted by industry.
Okay. Next question is, can the MS2A be used for ground fault testing?
So this is kind of related to the previous one. The NEC 230.95 code says that NEC National Electric Code Article 230.95 says that the maximum delay that can be set is 1200 amps. That's the pickup value that can be set on the ground fault. So if you go with either 1.5 times or 2.5 times that, you get the maximum delay, the maximum pickup value, the maximum test current that you need to inject during the ground fault test. So I can't remember the specs for the MS2A off the top of my head, but if the specs are not enough, then you can either reduce the ground fault pickup, as it applies for any other test set that you may have. If the capacity of the test set is not enough to do the test, you need to reduce the pickup value to be able to do the testing. So the ground fault pickups are generally low, but the maximum value that is set in the NEC code is 1200 amps. So in any case, you wouldn't need a test set that puts out more than 1200 times 2.5 or 1.5, whatever the factor is. You won't need a test set bigger than that. A smaller test set would work.
All right. Next question is, when performing primary injection testing, should the current value be supplied at 2 times the measured pickup value or 2 times the rating of the breaker or plug?
So the long time pickup value is set as a percentage of the rating of the plug. So which is usually pretty close to 100%. So for example, on a trip unit, you can have the long time pickup value set at 0.5 times the rating of the plug, 0.75 times the rating of the plug, 1 times the rating of the plug, as was the case in the example in which we discussed the long time test. We put the pickup at 100% of the rating of the plug. So the pickup value is set, could be set as a percentage or equal to the rating of the plug, and then the test current needs to be twice the pickup value. So in the example that we discussed, the pickup value was equal to the rating of the plug, and the test current was selected as twice the pickup value or twice the rating.
Okay. It looks like those are all of the general questions that have been sent in. We have a few that are really specific that we'll get back to the attendees on. So at this time, we're going to go ahead and close out this webinar. Thank you all for attending. If you can please remember to answer the survey, that would be excellent. The survey also includes a field for you to request, again, a demo or quote if you're interested. Thank you all again for attending, and have a great weekend.